Hey, good afternoon, everyone. Can you guys see me and hear me? Awesome. Thank you. Okay, apologies for the couple of minutes of delay. I could not connect to the internet in my normal room, so I've had to make some adjustments, but I am here now and we are going to finish up chapter 6 so that you guys have all of the information that you need for exam 2, which is coming up on Monday. Before I get started with some announcements, I just want to point out this block here. I have additional office hours today from 2:30 to 3:30 p.m. via Zoom, and you can find that link on your syllabus. In terms of announcements, I've created a stereochemistry practice worksheet. A lot of folks have kind of expressed interest in getting a little bit more practice at this, and I think everybody can always use practice in assigning R and S and defining isomeric relationships. So this is just for your own practice to do on your own. If you look in the modules under chapter 5, I've put this right at the top there. So right now you can go in and download that worksheet and try this out to help practice chapter 5. And I will be posting an answer key for this tomorrow. I will also be posting additional resources on Canvas related to exam 2 in kind of a separate module, the same way I did for exam 1, and those should be up by the end of the day today. Related to exam 2, as you guys know, it is on Monday. It will be kind of taking the place of our regular class time on Monday, so we will not meet as a class on Monday. It is going to cover chapters 4 through 6. Just like in exam 1, it's going to come in 2 parts. The first part will require the Respondus lockdown browser, and each part will be timed and each part will be completed in one sitting. And just like exam 1, there will be a window that you guys will get to complete this. The exam will open at 8 a.m. on Monday, and it will stay open for you guys until the end of the day on Tuesday, so that you can choose whatever timing works best for you to take that exam. You could take it during our 1 o'clock time period on Monday, or you could take it at any point, but it must be finished by the end of the day on Tuesday. Just a reminder about resources. You can, of course, stop by my office hours today, and also the CLC still has drop-in hours on today until 5 o'clock, and also on Sunday from 3 to 8. And you can find their full schedule at this link here for other days as well. And no class on Monday. That is correct in the text, in the chat box rather. On Monday, we will not meet as a class because your exam period will be open. And so you can use that time to take your exam, or you can use that time to study for your exam and take it anytime before the end of the day on Tuesday. And then finally, I'll let you guys read through this on your own to save time for actual chemistry stuff. But there are just some additional study tips and other resources for you guys as you're studying that you can check out when I post the slides. This third bullet here, there will be a free response section posted on Canvas as a practice. It's not up yet, but again, I hope to have that up by the end of the day. Okay, so in terms of the chapter, we're really almost done with it. We only have a few loose ends to tie up. So we're going to finish tying up those ends today. First, finishing off SN1 and then doing a comparison between the 2 mechanisms that we know. And then we'll circle back at the end and cover our alkyl halide synthesis reaction. I promised you just one new reaction for the synthesis of alkyl halides this chapter. So let's go ahead, get started, and pick up where we left off on Wednesday by talking about the SN1 mechanism for nucleophilic substitution of alkyl halides. The first couple of slides will be review, and then we'll get into new material, including the factors that affect the SN1 reaction. So here are the 2 types of reactions of alkyl halides that we've been talking about this chapter: nucleophilic substitution, which we finished up on Wednesday, and SN1 for an SN2 sense, and the nucleophilic substitution in the SN1 sense, which we started talking about on Wednesday and we'll finish up today. This reaction at the bottom is, again, where I want to keep our focus. This is the unimolecular version of nucleophilic substitution, meaning there is only one molecule involved in the rate determining step, and that is the alkyl halide. As a reminder, the energy diagram of an SN1 reaction reflects that it is a stepwise mechanism. It reflects this because you can see the two discrete steps shown in the energy diagram. The first step is the rate determining step, this uphill step, where we take our alkyl halide and we break that carbon halogen bond to create a carbocation and the leaving group, or the halide, which leaves with those two electrons as X minus. And then a second, more favorable step, which has a lower activation energy and is fast and exothermic. That second step is when the nucleophile attacks that carbocation to create that new carbon nucleophile bond. So take a moment in your minds and mentally compare this two-step energy diagram for the SN1 reaction to an SN2 energy diagram, which just goes up a mountain and down a mountain in a single concerted step. Okay, for the mechanism of an SN1 reaction, I just want to kind of summarize. I pulled together the content of kind of 3 different slides from Wednesday to review and refresh here. But it is, like we just saw on the energy diagram on the slide before, a stepwise mechanism. In the first step, we have formation of the carbocation, and there are some features that we need to keep in mind for that. This first step is the rate determining step, and that means we can write a rate law, which is proportional only to the concentration of alkyl halide. That also means, and if we look at this step, it should become clear, in this first step, where what we're doing is breaking this carbon halogen bond to give a carbocation and a halide that left with the 2 electrons, as is shown by this mechanistic arrow, this curved arrow notation, shows that the 2 electrons from that bond went with the iodide when it left. What we can tell from this is that the carbocation stability is going to be essential. It's going to be essential for determining whether or not this reaction can even work. So all carbocations are reactive species, but you need to have a stability associated with the carbocation to even get this reaction to work. And we'll talk about that some today in some future slides. Also, I want you to note that if there was stereochemical information at our original center, we've now created a planar carbocation intermediate, which means all stereochemical information was lost. And we have racemized that center if it was a chiral center. It is now 50% of one configuration and 50% of the other. And we'll talk about that a little bit in more detail as well on a future slide. Okay, so back to our stepwise mechanism. After we break this carbon halogen bond and we have these intermediates, the second step is that a nucleophile, for example, the solvent, if it's nucleophilic, like this methanol molecule here, the lone pairs on that oxygen are nucleophilic, and they can attack that carbocation to form our new carbon nucleophile bond. Because we have an actual free carbocation here in an SN1 reaction, this intermediate is strongly electrophilic. It is hugely electrophilic, which means that our nucleophile doesn't have to be very good at all. We can use a very weak nucleophile and it will still help this reaction. It will still be able to do this reaction because of how reactive carbocation species are. And in this case, we're not done yet because this product of the nucleophile attacking that carbocation isn't our overall product, because our overall product is a neutral species. So we just, as kind of like a bookkeeping step, have to take care of any protons that are out of place. So we're going to take our protonated product, that's the direct product of this methanol forming a new bond with our carbocation. And we're going to use another second molecule of methanol or whatever you have lying around that can deprotonate this oxygen to give you your neutral product here, and also a protonated methanol to keep our equations balanced. So here is SN1 in a nutshell, in a very kind of succinct and direct fashion. What I want to do now is drill down a little bit on the racemization concept. So as I showed you guys on the last slide, and as we saw a bit on Wednesday, carbocations are the key intermediates and the key mechanistic feature of SN1 reactions. And if we think back to chapter 4 about what we know about carbocations, that carbon is sp2 hybridized which gives that carbocation a trigonal planar geometry. That also means that in your carbocation, your positive charge is residing in this empty p orbital, which is going to have lobes that are both below and above the plane that's created by the other three substituents. So what does this mean in terms of the stereochemical consequences of an SN1 mechanism? Well, it means that our starting material, whether it was chiral or not, whatever the configuration was of our electrophilic carbon at the beginning, after we break this carbon leaving group bond, we have lost all of that stereochemical information. So once this carbon bromide bond breaks, we have a planar carbocation. And this planar carbocation doesn't remember what the configuration was from over here. It's planar. And so now the nucleophile, in this case, it's going to be ethanol. That ethanol can attack our carbocation from either lobe of this empty p orbital. And indeed, it attacks from both. And from the top lobe, you get one direction of the reaction and one particular configuration of that center. From the bottom lobe, you get the opposite configuration at that center. But again, our nucleophile has no way of distinguishing between the top and the bottom. So 50% of the time, it's going to go from the top. 50% of the time, it's going to go from the bottom. And what that means is that if this was a chiral carbon that we started with, it will get racemized. So a couple of things to consider here. If you have pure 100% S stereochemical configuration at this chiral center here, it will become 50-50 R and S. If you have pure 100% R configuration at this stereo center, it gives you the same carbocation intermediate, and you will get 50% R and S. What do you think would happen if you had a mixture of 80% S and 20% R at this starting chiral center? What would be the ratio in the end? What do you guys think? If you have 80% S and 20% R to start, 80% S and 20% R to start, they all make the same carbocation. So what do you think happens at the end? No, they don't switch. All right, if we have 100% S and it becomes 50% S and 50% R, we have 100% R and it becomes 50% S and 50% R, then it does not actually matter if this started out as 80-20 or if it started out as 60-40. If it started out as 72 and 28, that was really hard to do on the spot, then it would end up as a 50-50 mixture if it goes through an SN1 reaction mechanism. And that is because the R configuration makes this carbocation after the bromine leaves. But the S configuration makes the same carbocation after the bromine leaves. So it literally does not matter what your stereochemical configuration is here if you're going through an SN1 reaction. But Brittany, you are 100% right and on track if it was SN2. So yes, if you were doing SN2 and this was 80% S and 20% R, then all 80% of the S would invert configuration to become R, and all 20% of the R would invert configuration to become S. So they would switch. Did everybody get that? SN1, thank you, Brittany, for putting it in the chat. SN1, it doesn't matter what configuration you start with. They will come out as a racemic mixture 50-50. If it's SN2, every single molecule individually gets inverted. So if you start out with one pure enantiomer, then you get one pure enantiomer out of the opposite configuration. If you start with a mixture, then the amounts of each will switch. So, very good questions. Okay, so that's all I'm going to say about mechanistic considerations for now. The next thing I want to do is take our SN1 reaction and think about what are the factors that affect this reaction, right? We did this with the SN2 reaction. And if you remember back to the SN2 reaction, what you guys should all be doing right now in your head is thinking to yourselves, okay, for the SN2 reaction, we thought about the rate law. We know that the rate of an SN2 reaction is connected to both the alkyl halide and the nucleophile. So we talked about features of the alkyl halide that affect the rate and features of the nucleophile that affect the rate. So we can do the same thing with an SN1 reaction. The rate of an SN1 reaction is entirely, 100% entirely based only upon this step. This is the rate determining step here. Not that part, that's part of the second step. Only the carbon halogen bond breaking is the rate determining step. And so actually what I'm going to do is erase all of these circles and I'm going to draw a different circle to make it more clear. This is the rate determining step and it goes to both of these products. But the rate determining step is only what you see in this circle here. There's no nucleophile in that circle, right? So our rate determining step, because this is an SN1 reaction, is only dependent on our alkyl halide, only the alkyl halide. And so what that means is that the carbocation that is produced, which is a reflection of the structure of the alkyl halide that you started with, is going to be a major factor in determining how our SN1 reaction goes. The more stable carbocations are going to require less energy to form, and so those will be the more favorable SN1 reactions. So if all of these R groups here are carbon substituents, that reaction goes really well. If they're all hydrogen substituents, that reaction really actually does not go at all because you cannot make the carbocation. There's nothing to stabilize that carbocation. It's way too high energy to even form. So you want to form a stable carbocation, and then that carbocation can react with the nucleophile. But again, this nucleophile doesn't come in until after the rate determining step. So what's the other thing that we need to think about in the rate determining step? Well, one thing we made is a carbocation. The other thing we made is an X minus, right? So the better our X group is at leaving, the better our reaction will go. Now, in the next couple of slides, I will drill down on this top one, and then I will go into some more detail on this second one. So you'll see these things over the next couple of slides. But again, when we're talking about these factors that affect SN1 reactions, we're talking about the factors that can affect a rate determining step, which means only the factors associated with an alkyl halide. Okay, so for substituent effects, hopefully it made sense to you guys in thinking that if we need to form a carbocation, then forming a more stable carbocation will be the easier pathway to follow. So what do I mean by that? Well, we saw from chapter 4 already that carbocation stability is increased with increasing substitution, right? And we saw that there were two reasons for this. One is induction, stabilization of this positive charge through the sigma bond electron density distribution. We also saw that another reason that substituents help is because not just the sigma bond framework through bonds, but also through space, there is a capability of a neighboring bond. So bonds that are 2 bonds away from our carbon in question can help to stabilize this MTP orbital by sharing a little bit of electron density with it in a process known as hyperconjugation. This should not sound new to you guys. We saw this in chapter 4, but it really comes into play here with SN1 reactions because we need to form a carbocation. So if we need to form a carbocation, whatever we can do to stabilize that carbocation that we're going to form will help that reaction to go. And indeed, the reactivity of an SN1 reaction strongly favors tertiary carbocations for this very reason, and really actually does not happen at all with primary or methyl carbocations. Okay, the next couple of slides, I'm going to introduce a kind of crazy topic to you guys, and it's going to blow your minds a little bit. So I need everyone to pause, take a breath, and come back with me in a centered and focused way. This is going to be new material built on material you already know. but it's a little weird and it's a little crazy. So I need everybody to stick with me and follow through with what we have to show you here. Okay. In this reaction that I'm showing you here, this reaction is going to proceed through an SN1 mechanism, but it's going to have some weird consequences of how exactly it works. The substrate that I'm showing you here, if we react this with ethanol and a little bit of heat, the normal substitution, the normal nucleophilic substitution would put our nucleophile in the same spot where our leaving group was. And we can see that happens. That happens some of the time, and we get some product where our nucleophile ends up at the same position on the same carbon where that leaving group used to be. But we also get another product. We get a mixture. And in this case, the product that we get additionally has our nucleophile coming in on a different carbon. And so instead of coming in on carbon 2, it's coming in on carbon 3 here, if we number these from left to right. So you can see this nucleophile ended up in a place you might not have expected. So we need to think about how this can happen. And again, remember, we as chemists, we put together these mechanistic ideas to help us understand observations that we see in real life, right? The observation of racemization at a center versus retention or inversion of stereochemistry means something, and then we have to go figure out what we think it means and why. So because of examples like this that were observed in a lab, we need to come up with a theory that makes this make sense to us. And so here's the theory behind this. Carbocations can actually rearrange themselves to form a more stable carbocation. Well, what do I mean by that? Take a look at this alkyl halide and imagine for yourself what would happen if you break that carbon-bromine bond. What kind of carbocation would this carbon be, right? Would it be a tertiary one or a secondary one or a primary one? Think about it for yourself and think about what kind of carbocation that would be. So hopefully you guys can see if we break this and we put a carbocation here, this would be a secondary carbocation because it's bonded to 2 carbons. And so that makes it a secondary carbocation. That's less stable than a tertiary carbocation, right? So if there was a way that the secondary carbocation could magically become a tertiary carbocation, that's what it would want to do. And so what happens is that if you have this sort of a situation, a specialized case, that you have a more substituted carbon right next door, then you can actually undergo what's called an alkyl shift, where the smallest group from this neighbor carbon can jump over to the carbocation that was less substituted. It will take the electrons in the bond with it. So in this case, we're going to move this hydrogen atom here. We will move that hydrogen atom with the electrons that used to hold it onto this carbon, and we'll pop it off and put it onto the carbocation that was left behind when we broke the carbon-bromine bond. Now, when we do that, we make a new carbon-hydrogen bond here, and this carbon, where that hydride used to be, now has an empty p orbital and a carbocation, but this one would now be a tertiary carbocation, which has more stability. And that is the driving force for this shift, this alkyl shift, which if it's a hydrogen is called a hydride shift, and if it's a methyl group, it's called a methyl shift. But this alkyl shift occurs in order to generate the most stable carbocation that's possible. So I want to take a moment and use this to point out why we would not just do SN2 chemistry here. So if you wanted this product, why wouldn't you just do SN2 chemistry on this center? It's a secondary center. We know that's a little harder than primary, but that seems reasonable. But the problem here is that the nucleophile that we have available to us is a very poor nucleophile. It's not an O- sort of a situation. It's just ethanol. It's fairly stable. It is not nucleophilic enough to go and poke that carbon-bromine bond and make it break. We have to wait until this carbon-bromine bond breaks because of the heat. And then once it breaks because of the heat and we have a carbocation generated, then because our carbocation is a good electrophile, our nucleophile doesn't have to be great. It can just be so-so, All right, so I want to show you on the next slide mechanistic arrows for what I'm talking about here, because I think that'll also help drive this point home. These are going to be the mechanistic arrows that you can use to show these rearrangements. So I've written these out here as hydride, methyl, or alkyl shifts. Hydride if it's an H, methyl if it's a CH3, and alkyl if it's really any other big group. Okay. This is a slightly different substrate, but a similar concept. In this case, it would have been a primary carbocation. If we had asked this carbon bromide bond to break, it would have been a primary carbocation. And that is even less stable than a secondary carbocation and actually cannot form. And so in this case, what we have is a methyl shift, which is a specific kind of alkyl shift. And what happens is that the methyl group moves with its pair of electrons to help bump off this carbon bromine. So when that happens, the two electrons of this bond are just going to jump over into this position. And that would force this carbon bromine bond to finish breaking, because otherwise you would have more than 8 electrons around that carbon. It'll also leave behind a gap in this carbon, which is the carbocation now. That now, because it's on this carbon as opposed to this carbon, now it's a tertiary carbocation. And that has stability associated with it that helps this process to happen. And so now your nucleophile, your methanol, your ethanol, whatever your poor nucleophile is, can attack at this position and form your new carbon nucleophile here. I want to point out, I've said this, but I want to make sure I write it on the screen so you guys can see it, that the smallest group on the carbon is going to be the one that moves. And this should be intuitive, because if you think about picking up the bond and having to shift it over in space, if that's just a hydrogen atom moving with its 2 electrons, that's going to be easier to move than a methyl group. And a methyl group would be easier to move than some big long chain, right? So whatever the smallest group is on the neighboring carbon will move or shift over. If it's a hydrogen, we call this a hydride shift, because the term hydride literally refers to a hydrogen atom with 2 electrons. So this would be a hydrogen atom with both electrons in the bond moving with it. And the example of a hydride shift was on the previous slide. Okay, so that covers this weird rearrangement. I do want to say this doesn't happen all the time in SN1, right? Like SN1, most of the time is going to be straightforward. You make a carbocation and then you put your nucleophile where the carbocation is. So this rearrangement scenario is the exception to the rule, but it happens often enough that I needed to just spend 5 minutes talking about it, which, because I spent 5 minutes talking about it, probably means that you might see a question about it on the exam on Monday. Okay. The other factor affecting SN1 reactions, I don't know where my 1 went here, but I'll try to fix that before I post it, is the leaving group. And this turns out to affect both SN1 and SN2 because it's part of the alkyl halide, and that's part of both rate equations. But I just want to take a moment and point out the features that you could have in really good leaving groups. And this should make sense intuitively. You don't need to memorize these. It should make sense intuitively that the best leaving groups are going to help either an SN1 or an SN2 reaction go. And the best leaving groups are going to be things that are stable after they leave. And remember, the leaving groups are going to be leaving with the 2 electrons in the bond, right? So that could mean that they have electron withdrawing groups or are electronegative to help stabilize that charge after they go. You want them to be not a strong base. You want them to be stable. So like these halides are good leaving groups because they're weak bases. They're the conjugate bases of strong acids. They're weak bases. Anything you can do to stabilize this leaving group will help. So polarizability helps to spread that negative charge or the electron density out over a broader area, which is stabilizing. Or in the case of these kind of specialized groups, which again, I am not ever going to ask you guys to remember or generate, but if I show you one, you should be able to see that this negative charge can be stabilized by resonance to 2 positions here, to 2 positions here, and to 1 position here. So the resonance stabilization will also help with that. I think that covers us for SN1. So what I want to do now with the remaining time is spend about 10 minutes comparing SN1 and SN2, because that's going to be something we have to do. And then at the last 10 or so minutes of class, I'll talk about a new way of synthesizing alkyl halides, which is actually a way you know already. I'm just going to take it a little bit of a step farther. So in thinking about comparing SN1 and SN2 mechanisms, we've been talking lately mostly about SN1 mechanisms, these unimolecular nucleophilic substitution where the alkyl halide is the only thing involved in the rate determining step, and that first step involves the carbon halogen bond breaking. But we also spent some time earlier this week talking about bimolecular nucleophilic substitution, or SN2, where that nucleophile attacks the electrophilic alkyl halide directly. So you need both molecules involved in the rate determining step. This reaction goes in a concerted fashion where your bonds being formed are happening at the same time or in concert with the bonds being broken, as opposed to SN1 where you break one bond, you break it completely, you have an intermediate, and then after you get this intermediate, you form a new bond in a stepwise fashion, as opposed to a concerted fashion. Okay, so I want everyone to take a moment and notice both of these reactions involve taking an alkyl halide and changing out a carbon halogen bond for a nucleophile carbon bond. Both of them involve a nucleophile, both of them involve an alkyl halide electrophile, and both of them get to a place where your product has a nucleophile carbon bond instead of a carbon halogen bond. So that means that we need to be able to, as chemists, think about if I put an alkyl halide and a nucleophile in a pot together, which of these two mechanisms is going to be the likely mechanism? Because that'll really make a difference for if we care and if we want to get stereochemical outcomes that matter, or if we want to get a racemate. Okay, so here are the things that distinguish these two mechanisms from each other. I'm not going to spend a lot of time on this chart because we've talked about all of these things individually for each type of mechanism, but I'm going to just take a moment to point out a few things and then introduce another couple of concepts to you guys. So for the SN2 reaction, the bimolecular reaction, where the nucleophile has to come and meet the electrophilic carbon in the rate determining step, the substitution patterns favor less substituted, right? This is exactly opposite of SN1, where you're breaking a carbon halogen bond and you're creating a carbocation intermediate, and that carbocation intermediate will be stabilized the more substituted it is. So the trends here for the substitution pattern of the carbon that is holding that halogen, right, the electrophilic carbon, that is going to be by far your biggest clue about which way this pathway is going to go. Okay, that's where you should start. And really the top two lines here should be able to help you figure this out in like 90 or 95% of the cases. But the place you want to start, by far, always, the place you want to start is what is the electrophilic carbon's substitution pattern like? If it is a tertiary carbon, you have no choice. You are going to do an SN1 reaction. You cannot even get a nucleophile into the backside of a tertiary carbon, so you cannot do SN2. It's not even on this list on this chart, right? If you have a primary carbon, then chances are you are almost certainly going to do an SN2 reaction. And the only exceptions to that would be if you don't have a strong enough nucleophile to do this. But if you have a low substitution pattern, most of the time you're going to be doing SN2 chemistry because your nucleophile will be able to access the electrophilic carbon. Okay, let's look at the second line of this chart because that's going to be your backup system for checking your decision about SN1 versus SN2. Just remember that the bimolecular SN2 involves both the alkyl halide and the nucleophile in the rate determining step. So if you have a poor nucleophile, you can't get this reaction to go very well. So if you find yourself in a situation where you have an alkyl halide that makes you think it's SN2, but then you have a poor nucleophile, like a neutral molecule, like ethanol or methanol, those are poor nucleophiles, then you need to think about, well, maybe it does do SN1, and maybe it's one of those weird rearrangement examples that we talked about on Friday. Okay. Polar and protic and aprotic solvents, I'm going to talk about it in the next couple of slides, so I'm going to skip them here. But the other three entries here on the bottom of the chart are things that we've talked about at great length already. For SN2, the rate of the reaction is bimolecular, so it depends on both of these species, whereas for SN1, the nucleophile is not involved at all. We've talked already a lot about the stereochemical inversion that happens with SN2, as opposed to the racemization that happens with SN1. And we've talked about rearrangement products now for SN1. In SN2, there's no chance to have a rearrangement because it is a concerted reaction where those bonds are being formed and broken at the same time. Okay, for the solvents, I want to take just a couple minutes and discuss this notion of solvents and basically point out that you don't see solvents listed in the rates here, right? So solvents are not part of the rate determining step, but what solvent choices can do are to stabilize the species that are involved in the rate determining step, or to destabilize the species that are involved in the rate determining step. So I'll show you that briefly on the next couple of slides. Okay, here is an SN2 reaction, and right now I'm going to show you what happens if you use a protic solvent. This is going to be like an alcohol solvent. Any solvent that has a hydrogen bonded to a strongly electronegative element. And what happens is that if you have polar protic solvents in SN2, it's really bad for the reaction. It's bad for the reaction because what that polar protic solvent will do is hydrogen bond its way all the way around your nucleophile and sequester your nucleophile. What this does is stabilize your nucleophile. It makes it more stable and therefore less reactive. And so your nucleophile is not as free to be a nucleophile and go attack the electrophilic carbon. So you do not want a protic solvent in your SN2 reaction if you can help it. What you do want instead is what's called a polar aprotic solvent. So these polar aprotic solvents do not have acidic protons. So they still have hydrogen atoms, but these hydrogen atoms are attached to atoms that are not electronegative. So these are not acidic. And so these are not considered protic solvents, right? Protic meaning proton. They have hydrogen atoms, but not necessarily things that can generate protons. And these are three examples. If you have these polar aprotic solvents, then you get the awesome benefits of having polar solvents to help stabilize the charge buildup in the transition state, but without the hydrogen bonding that would sequester your nucleophile. So if you have an SN2 reaction, it's favorable to have this aprotic solvent situation. Okay, I'm going to spend like literally only 30 seconds on this slide because it is just a brief feature that I need to introduce because it may show up in your second semester courses. I'm not really going to talk to you about this beyond this slide. There are these things called crown ethers. You guys know what ethers are from chapter 2 functional groups. It's an oxygen bonded to a carbon on both sides through single bonds. If we arrange a bunch of ethers in this fashion in a cyclic molecule, you can see this kind of looks like the shape of a crown. And what this does is it orients all of these lone pairs of these oxygens in a way that can stabilize cations, singly charged cations. And what that does is that if you imagine nucleophiles like X minus that would be ionic, if they, for example, if you wanted to use potassium chloride to get a fluoride nucleophile, that potassium ion would do the same thing that we saw with the polar protic solvent, that it would be ionically bonded, not hydrogen bonded, but ionically bonded to the nucleophile and prevent that nucleophile from attacking the electrophile. But if you put your KF in with this crown ether that sequesters the cation, the potassium cation, that leaves behind your halide as what's called a naked nucleophile. So it strips away the cation that goes with your anionic nucleophile, makes it a better nucleophile, and promotes this SN2 reaction. Okay, that's all I'm going to say about crown ethers. They have different sizes for different cations, which is kind of neat. But this is just something that is a kind of a side note, but may show up if you take this second semester with somebody that's not me. You might see it. So I wanted to show you guys. Okay, we've been talking about SN2 solvent effects. I want to talk briefly about SN1 solvent effects. And that is to say that polar protic solvents now in this case are the best solvent, because what are you trying to do in an SN1 reaction but create a carbocation and an anionic species? And so now that same hydrogen bonding that was messing you up before is favorable because it's stabilizing the intermediates you're trying to get to, right? So your hydrogen bonds are going to stabilize your leaving group after it leaves. And because it's polar, your solvent's polar, it'll also help to stabilize the carbocation that you form. So why aren't we worried about the hydrogen bonding that our polar protic solvent is going to do to the nucleophile? We still have to have a nucleophile. It still has to attack. So why aren't we worried about that? What's the rate determining step of an SN1 reaction? And is the nucleophile involved in it? So the rate determining step is right here. Whatever we can do to help this step helps the reaction. And yeah, our polar protic solvent is indeed probably making our nucleophile not as good as it would be. But in the case of SN1, it does not matter. In the case of SN1, the nucleophile is irrelevant to the rate determining step. So having it be not quite as good as it was, no big deal. So polar protic solvents are where you want to be for SN1 reaction. Okay, your book has a chart too that has all of these factors listed out. I am not going to read through this, but I just want to draw it to your attention so you can read through it on your own. But look, it says the same things that I said. Here's SN1 showing the tertiary and secondary, SN2 showing the lower substitution patterns. Same stuff on this chart, but take some time and read through it on your own. And I'm going to spend the very last couple of minutes of class. I need to cover a topic that we skipped, which is the synthesis of alkyl halides. Don't worry, you guys already know this. Let me say that again. Don't worry, you guys already know this. I'm going to take concepts that we learned in chapter 4 and just extend them a little bit. So let me go ahead and do that real quick. We can prepare alkyl halides. So notice I'm switching gears. Instead of reactions we can do with alkyl halides, which so far are nucleophilic substitutions of 2 different types, we also need to know how to make them. If we want to use them, we need to know how to make them. So we learned about this already in chapter 4. It's called free radical halogenation or free radical chain reaction. I'm going to extend that just a little bit to a specialized case of allylic positions, and we'll see what that looks like in a minute. This slide is literally from your chapter 4 slide, so I'm going to go through it real fast to make sure I get to the new goodies. In our free radical chain reactions from chapter 4, first we're going to create a chlorine radical, and then we're going to have 2 propagation steps, right? 2 propagation steps. These are single-headed arrows because we're dealing with radical chemistry and single electron chemistry. After our 2 propagation steps, which you guys should review on your own, we're going to regenerate that chlorine radical, which goes back in, hence the chain reaction part of this. And don't forget, you also have termination steps. Also from chapter 4, remember that when we had a choice between a secondary hydrogen atom and a primary hydrogen atom, the secondary radical that would be generated is more stable than a primary radical that would be generated. So the pathway to get to a secondary substitution, a secondary bromination, is faster than a primary or any kind of halogenation. So even though there are 6 of these primary hydrogen atoms and only 2 of the secondary, the products favor the secondary. Hopefully that's all familiar. And hopefully this stuff is familiar for you guys too. Radicals on the carbon atom are more stable the more substituted they are. That follows carbocation chemistry exactly and perfectly. And also from chapter 4, we've also talked about the allylic position. So here is a slide also directly from chapter 4, where we have the allylic position, which is the carbon directly next to a double bond. And because of resonance, that position is stabilized. So as you can imagine, if we want to brominate at that position using a radical bromination, that's an awesome reaction to do because this radical is really stabilized. So what that looks like is this. Here is an allylic bromination. In this example, there are 4 different allylic hydrogens that could be pulled off during our radical bromination step to put a carbon radical at either of these positions. It turns out all 4 of these are identical because of the nice symmetry we have in this molecule. And I'll show you a little bit more of this on the next page. But we end up in the same place because of the symmetry. I'm going to show you an example where we don't end up and we get in the same place. We get a mixture of products. But this point here is that bromination occurs really well next to a double bond because of the stability of an allylic radical. So here is mechanistically what we're talking about. We can take off any of these 4 allylic hydrogen atoms to get this radical, and that radical can react directly with the bromine to get this product. But there's resonance. There's resonance. So also this radical here, the resonance form of this radical could react to get brominated. In this case, because of the symmetry, it still gets you to the same molecule, but I'm going to show you on the next slide an example that's different. And just in general, don't forget about initiation and termination steps. Stick with me one more time. This is the last slide. I know I'm going to go over by about 1 minute. I'm sorry, but this is important. If you want to do a synthesis of an allylic bromination, you have a problem because the bromine that we need to use in this reaction can react with double bonds. You guys haven't learned that reaction yet because it's a future chapter, but I'm telling you that happens. So what we have to do is use a new reagent. This is the only new thing that I'm going to be teaching you in this chapter for synthesis of alkyl halides. We have a new reagent. Whenever you see NBS for N-bromosuccinimide, you know that's going to be a radical halogenation and probably an allylic one. And what this reagent does is that it generates molecular bromine in your reaction flask in such a low concentration that this problem up here is not a problem. So what this does is it keeps the concentration of bromine overall low and avoids side reactions. And then the last thing I want to show you is just an example where you can see the mixture of products potential that I mentioned on the last slide. So there are 12 hydrogen atoms in this substrate. Any of these will give you the same radical at a terminal carbon here, but because of the allylic resonance of that radical, it could also end up being on one of the carbons of the double bond. And indeed, you see bromination in both positions, both at the original radical and the resonance position of that radical. So I encourage you guys to take a look at this carefully and think through the mechanistic implications here, think through the mechanism of this reaction. And that is where I'm going to stop, and I'm happy to take questions. And I'm sorry I went a minute over, but I got here 3 minutes late, so hopefully that makes up for it. Woo! Questions, happy to answer them. Thank you guys. Yes, I will make the quiz 4 grade available. I have already made it so you guys can go in and see the answers to quiz 4. So you can go into your quiz 4 and look at your answer and what the right answer is, but I will make the quiz 4 grade available shortly. If not before office hours, I'll try to get it done while I'm answering questions in the background during office hours. Sorry about the delay. Okay, thank you guys for making it through the end of chapter 6. And John, don't worry about being late. There were some major announcements about the exam. I will try to do a recap briefly here. And then I will also be posting the slides, but let me just go ahead and.
We have a very, very nice contractor that knocked out our internet. I don't want him to hear me.
I was actually 2 or 3 minutes late anyways, because I also had internet difficulties. So let me find my way back to sharing. Okay, can you see my slides again? Okay, first announcement was that I made a stereochemistry practice worksheet. This isn't for points or anything like that. It's just so you guys have another way of practicing. And I stuck it under the chapter 5 module. And so you can download it there, and I'll put the answer key over the weekend for it. That's one.
Thank you.
And then the other major announcement, you know already that the exam format is going to be like last time, but this is the other major announcement. I'm going to open the exam at 8 a.m. on Monday, and that window will be open until the end of the day on Tuesday. It does have to be completed in one sitting once you start, but that's the window that you have to do it. And the rest of the stuff is, you can read through it on your own. It's not anything. Oh, I have office hours today from 2:30 to 3:30. That's the other major thing. Okay. Yeah. And I'll post it slowly in your own time.
Thank you so much.
Yeah, you're welcome, John. I'm sorry to hear about your contractor.